Hello, and welcome to another session. In this one, we're going to talk about the AWS Well-Architected Framework and its reliability pillar. My name's Kami, and let's get started. So I'm going to start by similar thing. We're going to start by looking at the design principles of the pillar, and then we'll go into the tool and we'll go through all the questions and then how to answer those questions in the Well-Architected tool on the AWS console. So when we talk about reliability, we're basically focusing on the aspect of an application that you've got running in AWS and how reliably your users can access that application. So in order for an application to be always available, you do want to make sure that you've got the ability to automatically recover from failure. So if there is a problem, then you've got enough monitoring in place to know that there is a problem going on, and then you have automated scripts that can go out and take action to bring that application back to a functional state, or at least to a point where your users are not going to get an error page. Maybe they can get a message that says, hey, the application is not available right now, but it should not be just an error page essentially. And that's where identifying your key performance indicators and knowing what exactly is of business value, that if that indicator goes down, then that means there is a problem, or your users are experiencing a behavior of the application that is not expected, or that is not what has been committed. And so you want to take action on that. So these are the things that should feed into how you automatically recover from what is called a failure. A failure doesn't necessarily mean it's completely down. It could just mean that you've gone through the threshold of what is acceptable performance levels or availability levels for your applications. Another aspect of it, of reliability, would be to test your recovery procedures. Many times it happens that we create applications and we put them out there, but we don't take the time to confirm whether, if something goes down or if there's a problem, that we would be able to recover from it. And so that's something that has to be consciously added into your thinking, as well as the process that you have in an ongoing operational model. The other architectural impact of reliability and getting to a more reliable system is being able to scale horizontally for your workload. What horizontal scaling means is that you can add on other servers into your mix that can serve the application if one of your servers has a problem. And this distribution model requires you to have your application built in a way that can support different servers being added in or being removed from the pool without impacting your users, or having to go through a big configuration change in order to make that happen. It should be easy to just throw in additional resources into the pool, or when they're not needed, just remove them without having to make any other changes. That's different from what's called as a vertical scaling, where you're basically increasing the size of your resources, increasing the size of your servers in order to handle more requests and demand coming in. That is not something that we prefer to do in the cloud. If you're designing something for a cloud-oriented model, then you do want to lean more towards having a horizontal scaling model. That way you can build in your layers of a load balancer, put in all your resources behind that load balancer, and then let the load balancer handle how many resources it brings up and down as part of an availability group, and all those different aspects or different features that are available in AWS start to then play together in order to make this a really highly reliable system that you would have, that you don't have to worry too much about it and do manual work on. It gets handled by the way the system actually is designed to work. The next one is around capacity management. So when we designed things on-prem, we had to think about, okay, how many users are we expecting? What sort of workload, how much RAM would we need? How much CPU would we need? And not just that, but also in terms of the network pipeline and all those different aspects of of your infrastructure had to be thought about and designed in that manner, and you had to provision for the maximum workload that you would have to support. Now, on the cloud, we don't have to think about what we may anticipate or expect to have at a certain point of time. We can actually use data and metrics to figure out exactly how much demand is coming in, and based on that, what specific resources are needed to support that demand. And when that demand goes up, you can add on more resources, and when that demand goes down, you can remove those resources. And so you're not really thinking about your thresholds and maximizing the resources available to an application, but rather you're optimizing that to make it available exactly as what is needed. But that also has an implication that you have to know about how far you can extend something in an automated fashion. And so being aware of what those limits are, where some quotas may be enforced upon a particular service, like say S3 will not allow you to have more than 1,000 buckets just by default. And so if you're creating an automatic application where you're just churning out more buckets based on some event that's happening, then be aware that when you hit that 1,000 bucket limit in that account, you would not be able to create more buckets. So some of these quotas, you can beforehand reach out to AWS and ask them to increase that limit if it is a valid use case. Or in some cases, you may just choose to have a different design in place so that you're not going to be hitting those quotas. So that's kind of part of you have to be aware of, so that you can design your application and your architecture in a way to support or stay within those quotas and constraints. The last piece is around managing change in automation. Whatever changes that you make, you have to make your changes through your infrastructure as code, but also those changes that are happening to your infrastructure as code should be tracked and reviewed so that you know exactly what is coming in, what is changing, and what change may at some point cause a problem, so that you can go revert that change and what exactly scope it down to what has to be fixed. That way you're not just going all over the place trying to figure out what went wrong and how do I recover from this. So these are some of the design principles that you can keep in mind as you're thinking about reliability and how to maximize and optimize reliability for your application as compared to all the other pillars that we're talking about. All right, so now let's switch to the tool itself. The reliability pillar has, I think, 13 questions. So we're going to go through them and talk about what each of these options mean. The first one, it goes back to the service quotas and constraints topic that we were just talking about. In this case, being aware of what your service quotas and constraints are, it's obviously an important thing. If you know that your network has a certain bandwidth and you cannot exceed that, then that's going to help you design your application, set expectations, and communicate appropriately to your users of what to expect when you're going through that particular network pipeline where you've got a constraint on it. Or if you have service quotas, then you can design accordingly within those. Managing your service quotas across accounts and regions is, again, part of the designing and being aware of the service quotas piece. If you know that you've got certain constraints that will come into your environment based on the way your application works, and you're going to hit some quotas in a certain account or in a certain region, then you may want to plan for having additional resources available in a different account or in a different region so that you're not getting limited by those service quotas. And then accommodating fixed service quotas and constraints through the architecture. This is similar, to the previous one. One is making sure that you are able to manage those quotas by requesting an increase or distributing them across different accounts and regions, but then being able to accommodate those so that when you do hit a constraint, at that point your architecture automatically is able to expand out into a different region without having to redo your entire work or the way the application functions. And then knowing when to make that change is going to happen through monitoring and managing those quotas. When you're about to hit it, so you've got API calls that are actually figuring out, if you're getting close to your quota limit, and so then you can take action. And that's the next piece where I'm around automating that quota management, so that when your APIs do inform you that you're about to hit your quota limit, you can take action to either increase that quota or expand it out into a different account or a different region. That way, you're not going to be hitting those quota limits. And then when you're creating this kind of a monitor and an automated response to it, just providing sufficient buffer in between, so that the time it takes to add on additional quota, sometimes when it requires a manual review from the AWS side, just keep that in mind, that it could take up to 2 or 3 business days for AWS to review your case and come back and say, yep, you're going to increase your quota, or they may ask for more information. So if you're very close to your limits, and at that point you start the process, you might just hit your limit by the time AWS increases it. So you want to be aware of how much time it may take for these limits to increase, or for your expansion to happen into a different account or a different region. And so factoring that into the buffer that you need to keep in place before you start kicking off the automated quota management process. All right, so the next question is planning out your network topology. So network is another area where you could easily get constrained, and that could impact how your application is responding, whether it's available or not. And so being able to plan out your available IP space, especially when you break down your account into multiple subnets, allocating sufficient IP across all of the subnets, so that when you're horizontally scaling, let's say as an example, EC2 instances or lambdas that require to be in a VPC, they take up an IP address. Those there should be sufficient IP space available for that expansion to happen. If you don't have enough IPs, then you won't be able to instantiate that next EC2 instance, and that can then affect the reliability of your application. Also, the connectivity that you have between your workload endpoints and wherever else it's getting its backend information from. So let's say you've got connectivity between your on-premises environment and AWS, then that connectivity should be done in a highly available manner. That way, if one of the connections go down, which in a network it's inevitable, then the other one can take over, and it doesn't break that connection, which would then obviously make your application unavailable. The next piece, having sufficient redundant connectivity is also part of the design that you put in place when you're talking about connecting different networks and different endpoints together. And then we talked about ensuring IP subnet allocation. And also the next piece is around the preferring a hub and spoke topology over many-to-many mesh. This is more of a network design concept, where a many-to-many mesh is when you do different you've got multiple networks across multiple places, but then you do point-to-point connections between each of these different different networks, so that you can control from a security perspective and traffic flow perspective which network is allowed to talk to which one, and you're only providing a connectivity between them. That becomes a many-to-many mesh model, as opposed to a hub and spoke model where you've got a centralized resource or a network which becomes your hub network, and all of the different networks that you want to be able to connect to are connected to this one central hub network, and all the other spokes are controlled from a security and routing perspective by the hub network. So that's more like a switch model, where you've got traffic coming into only the hub, and then depending on what's allowed to go into a separate different network, that traffic is either routed or it is rejected. So that model, especially with something like the AWS Transit Gateway, is a preferred approach over what we used to do in the pre-Transit Gateway days, which was creating multiple VPC to VPC connections. And then the network connectivity piece has another connotation to it, which is you have to plan ahead for and make sure that the private IP address ranges that are being used across all these networks, especially the ones that need to talk to each other, they are not within the same IP ranges. That non-overlapping IP address range concept is important if you want to be able to route traffic from one network to the other connected one. If there is any kind of IP address overlap, then those two networks will not be able to talk to each other, and obviously that's going to impact your application and how it's going to operate. So this is all part of the planning work that has to be done, before you actually start instantiating your infrastructure and your environment within AWS, or start connecting with your on-premises networks or even partner networks out there. So the next question is around your actual workload and the services that you have as part of that workload. So this is more focused on the architecture of your workload and how you segment the different services. So if you have a workload that is compatible with the microservices model, then being able to build out your entire functionality as separate API services, even within your application. It doesn't have to be an API that's exposed to the outside world, but just within your application, if you are able to segment it out, then it's easier for you to confirm and make sure that each portion or each separate service is operating the way it should, and you're containerizing or containing the problems or implications of one portion of your code not operating as expected. And that obviously feeds into how reliable your application is, because if something does happen, it's that much easier for you to bring back it to an operational state, and so the reliability goes up. Building services focused on specific business domains and functionality. That's another best practice that that we've seen work very well across multiple applications. That instead of focusing on technical specificity of what a particular service does, if you focus more on the business domain and functionality that your users need, then you're able to separate out what different kinds of users and different use cases are being clubbed together into a specific service. That way, even if a service does go down, it's a specific set of users or functionality that is impacted, that's visible, and so you're able to come back and fix those issues instead of something that would have been just an underlying technical service which causes a problem, and it shows up in 15 different places and 15 different functionalities, and then now it's harder to figure out where the problem came from, and that takes a longer time, and your availability of the application can take a hit. So this design pattern is seen as something that's more efficient in managing and maintaining your code and responding back to problems. Providing service contracts per API, it's just an internal best practice that behave with your internal API also as if you were doing a commitment to an external audience, that you will maintain an API in this particular fashion. Your interface will remain exactly the way it's defined. It will meet certain performance criteria. It will meet certain design changes. Will be done with a certain level of let's say advance notice, or information being available through, say, a development API that's released earlier than the production changes happen. And so these are all the kind of things that we would normally do when we have one organization making an API available to other organizations. But typically we don't do that when you're doing it just within your team or within your application. But if you operate in the fashion as if each of your APIs or your services do have a contract around it, then even within your team, it makes each of these siloed APIs and services work in a much more reliable fashion. So that's another piece to bring into your teams and your mindset. The next one is it's not going to be relevant to all of the applications, but it is something that you want to think through, that if you do have a distributed system where you've got multiple components that need to talk to each other, then that's a distributed system. And so the interactions that happen within those those varied components within your application, making sure that those can talk to each other and are designed in a way that you prevent failures internally. And so, identifying the kind of distributed system you need, having loosely coupled dependencies, so that if one of the components is having a problem, all of the other components can still continue to do their work at least, and not get impacted with one component being unavailable. And then doing constant work to make sure that these different components are talking properly, looking at the logs, looking at any other errors that are coming out, making sure that there is sort of supervision of your application and all of the components that are talking to each other in that distributed system. That does require constant work. So, having somebody whose responsibility it is to perform that sort of oversight is an important aspect of a distributed system. So keeping that in place. And then making responses idempotent. Idempotency is the principle that if you call a certain function uh, with different environmental variables, it will always return the same response. So if you send it a certain set of parameters, you will always get back the exact same response. So the way it's helpful in the context of your application is you don't rely on a previous step or a previous interaction that had been done with the user to make the next uh, judgment or calculation, and but rather you rely on the exact parameters that are being sent to that to a particular function, and so that function will always operate in the exact same fashion. This is something that came from object-oriented programming models, that you create your functions in a way that you pass all the parameters to it. So each class and each method within that class is standalone in itself, and if you call that method, it will respond back with the same output every time, which is different from other scripting and programming paradigms where you would just in a linear fashion perform things in a certain manner, and you when you call a function, it expects certain things to be in the environment or loaded up in memory for it to do its work. And we want to design our workloads, our different components in a way that every time you send certain parameters to it, certain data points to it, it will respond back in a consistent fashion. This is something that's kind of built into the whole Lambda function as a service model, where every time you call a Lambda function, you have to send it all the data that is required for it to perform its work, and then it'll give you back the same consistent response every time. So having that design principle also as part of the different components of a distributed system makes it that much easier to have reliability baked into your architecture. All right, so the previous question was about how do you design to prevent failure. Then this next question is more around in a distributed system, how do you actually handle a failure? And so when there is a problem that happens within one of those components, then making sure that you've got a graceful degradation process or path available, so that if there is a problem in one area, the user is informed, or there are checks and balances built in, so that the other components know that, hey, let's say my database is not available, so I'm going to go to my cache and get back information from there, or I'm going to send back a response to the user saying the database is not available, and we can give you the last available information or data point, or you may just say this feature is not available. So those are all ways to handle the situation and inform the user about what's going on, rather than just throwing a message up there saying database not available, try again. The user doesn't know what to do with that. The next one is you can, if there is a problem going on, or you've got reduced capacity for your application to perform the work, you could even throttle risk requests, which means you could reduce the number of requests which are being sent back. So you can use the gate that's in the front of your application reduce the opening in that so that fewer requests come into the application, and then those requests are actually then being handled appropriately. Controlling and limiting retry calls. So again, sometimes if there is a problem happening in your backend, the front end user or your front end application may just keep trying again and again. And so being able to have a limit on how many times you can retry within a certain time period, at which point you need a certain cool off period before you can try again. Those sort of design principles will help you not get your component, which is already under pressure, will not get overwhelmed with more and more requests coming to it. Fail fast and limit queues. Again, these are all different concepts that you can use as part of your design to say, if there is a problem going on, I want to, one, get notified sooner than later, but then also I can have a limit queue built in. That way, there's a kind of a buffer being added into your components that even if there is a problem in the backend, there may be some sort of a queue being maintained that when the system comes back up, it can start processing those pending requests. Again, it depends on your use case, depends on the kind of application you're building. Many of these may not be relevant or applicable to your environment, and if that's the case, all you have to do is just say these best practices don't apply to the workload, check off those boxes, and you will still get to know how to build out reliability using all the other questions. So it's okay if some of these options or these best practices don't apply to your specific scenario. Making your services stateless where possible. This is very much in line with the idempotency concept, where if they're stateless, they have to rely on the parameters that are coming in and then responding back with specifically what was given to it. And then implementing emergency levers. This is if there is a problem, you need to have some way to go into the system and then start doing some fixes. That way, making sure that you've got a pathway to get into the application and you're not completely locked out of it, or you have some standby version of the application that's available that you can bring in and load that. That way, you're moving away from your primary application, but you're using this failover or backup application available, or some other way in which an emergency state in your scenario could be handled. So there's no one way to do it. It really depends on what's in your environment, but having thought through some way to handle an emergency is what this question is focusing more on. So it's just saying, have you thought about having some kind of an emergency process in place? And if so, then yes, you can check that box off. And if not, then this makes you think about what can be done so you can start baking that into your application. All right. So the next one is just knowing what's going on with your workload. Are you generating the right kind of data? So monitoring all the components for the different parts of your workload, and then putting it all together. So making sure that you've got the right metrics in place, but also you're collecting that information that will feed into that metric calculation. And then if there is a problem, then being able to send notifications and then automating a response if there is a real problem, right? So these are all things that go together into some kind of a monitoring system. And it doesn't matter whether you use CloudWatch or some other third-party system like a Splunk or Datadog. As long as you've got these concepts being used and being applied and information is being sent over to you when something is a problem, you can go ahead and check off those boxes. But again, these are all ways to make sure that you've thought through all of these pieces and you've got analytics to know over a period of time how information is trending, how your resources are trending, so you can actually take action on the information that's being shared back with you. And then just collecting the data is not enough. You have to conduct your reviews on a regular basis so you know what's actually happening within the system, and you can then make tweaks, take action on the information that you see, and then come back and review it again after some time to see if there was any impact from the changes that you made. And then the last piece is around making sure that you've got, that monitoring is not just of your application, but rather for an end-to-end tracing of requests through your system, starting from when the user makes the request or whichever application is making the request. It comes to your application, it goes through the infrastructure. So you have to track or trace the request through the entire full stack, all the way back to the response. That way you would know where exactly the problem is, not just within your application, but if it's something outside of your application, say on the database or on the network level. Having a full end-to-end traceability is going to allow you to be more proactive around responding back to where the bottlenecks might be. All right, the next one is designing your workload to adapt to changes in demand. This is more around the auto scaling aspect or the elasticity of your application. So, when you have to obtain or scale resources, is it being done in an automated fashion? Ideally, it's you leverage the features and capabilities that are baked into AWS services. But if you're not doing that, it may be some applications don't support that. And so do you have scripts in place? Do you have other tools in place that will actually automate it and not really send out a notification that, hey, we're running low on a certain resource, and then now somebody has to manually go in and make that change. If you're able to get to that point, try and push it over to the automated state rather than leaving it at a manual state. Obtaining resources upon detection of impairment to a workload. This is connected to the automation piece that we talked about. If a resource is being impaired, it's not completely down, but it looks like its health is getting affected. Maybe it's slowing down, maybe it's not responding, or it's intermittent in its response. When you detect that kind of a situation, just add on more resources. Don't try to figure out what's going on. Maybe you can do that as a separate activity, but before you do anything else, just add more resources. That way your users are not impacted, and then it gives you more time and more buffer to go figure out what was going wrong. Or obtaining more resources when you realize that there is more need, there is a higher demand, right? So being able to monitor and detect that there is a higher demand is going to also help you trigger that extra resource request, whether it's new EC2 instances, whether it's adding on another cached read replica of your database, whatever that may be relevant in your specific case. But being able to kick off that process upon detecting that more demand is coming in. And then load testing your workload. You don't want to know just when actual use cases happen in production that and find out whether or not your resources are scaling as expected. But using load testing tools, you can actually mimic your behaviors, your users' behavior, and you can actually these days you can use cloud load testing tools to even try out having, say, 10 times the expected workload that you have, or expected demand, and then see how far you can push your design and when it starts to break. So you know exactly at what point or at what kind of usage will your architecture stop being effective, and you may have to make changes to it. But until that time, you're good to go. Your system is going to support it. That load testing will give you metrics, data, and decision points that you can use to make changes to your application. So that's a very important thing. If you're not doing it today, I highly recommend that you add load testing into your process. Implementing change. So when we talk about making changes, anytime we make a change, it can impact the reliability of the application. So reducing the way a change can impact your application or making it more streamlined is going to help make your application more reliable. So these options or these best practices are basically designed towards that. Having a run book, a specific checklist of things that have to be done with every deployment, so you become more consistent. You don't miss a step. That if you miss a step, it may change how your application is going to function. So having a run book makes sure that even if you've been doing this over and over again a lot of times, you make sure that nobody on the team is going to miss a step. integrating functional testing as part of your deployment. So the best practice that that I would lean more towards is as part of your pipeline where you're going from one phase to the other, having functional testing that looks at whether or not the functionality is what what was expected, what a user will see. Is that going to be is that operating as was committed to the users, or made as part of the design? That should be part of the deployment. So you do your testing before you do the deployment, but then as soon as you make your deployment, you test it again in the post-deployment state to make sure that the functionality was not impacted. Similarly, having resiliency as part of the deployment, you make sure that if once you've deployed things and some part of your application is not working, then that auto scaling is functioning as expected. These are all things that you would test out before the deployment and then again after the deployment. Using immutable infrastructure. The idea behind immutable infrastructure is that you don't actually update an existing server, but rather you replace that server with a new instance that goes in. And that way, what it means is anytime you have to make a change, you're making a change in a new resource. You're applying the change into a new resource and then deploying that resource into your production environment instead of going in and modifying that existing previous resource. And because in the cloud, you're not really tied to any specific resource, it's all virtual machines. You can just terminate the old one and replace your pool with the new resources that are coming in, the new virtual machines, which have the updated code in it. And so that makes a big difference in how you modify your application. And that way the previous version is actually not gone. You may stop it for for the time being, or you may take it out of the pool and then replace it with the updated virtual machines. And if something does go wrong, you're able to revert back by literally replacing the machines back in the pool. And so this increases the reliability of your application, that if something went wrong, very quickly you revert it back. Your users might not even notice, and you're back to an operational state at least. And then doing all of this in an automated fashion. You don't want to be on the call. You don't want to be up all night trying to make these changes. Let a script handle that for you. That's an important aspect of being able to do this in a reliable fashion and a consistent fashion every time. All right, the next one is about backing up your data. So sometimes when things go wrong and you have to recover your entire application, the one thing that you cannot recreate, is the data. You can recreate all your resources, all the connections, everything that lies in between the user, but you cannot recreate the data. So making sure that your data is properly backed up and can be reproduced again as needed is an important aspect of your design and your process here. So identifying exactly what data should be backed up, making sure that that is getting backed up and it is being secured and encrypted when it is stored in your backup, so that if there is a breach, you're not getting impacted by data loss at that point of time, or um, having that incident becoming a bigger problem for you. Doing that data backup in an automated fashion, and then doing periodic recovery tests to make sure that whatever you are backing up is actually restorable. There have been times where I've worked with teams that have been doing backups. They've got the right tools in place to back up every time, and they've confirmed that the backups are working. But it was only at a point of a failure or a problem that they tried to recover from the backup, and they found that they were missing, say, maybe one file or a few things that should have been there in order for the backup to work properly. And so you want to find out those things not at the time of a problem, but earlier on. So you want to have this backup restore testing happening on a periodic basis. All right, and then adding in concepts of fault isolation to protect your workload. So what this does is, if there is a problem in one portion or one service within AWS, or one say availability zone, then you want to let that one problem not affect the rest of your workload or how it is responding back to users. So deploying the workload to multiple locations is an important aspect of that. So if you've got an application that can support, say, 3 separate servers that are responding back to user requests, then placing those 3 servers in different AZs will help you with that fault isolation, so that if one AZ goes down, you still have 2 servers that are available to respond back to the requests that are coming in. And then selecting appropriate locations for your multi-location deployment, making sure that if you've got users in the West Coast, then you choose your regions that are closer to the West Coast and not somewhere in, say, Europe. So those are the kind of things that you want to think about, like where your users are coming in from, and then identifying the different deployment locations based on what will make it closest to your users to have access to your application. Automate recovery for components constrained to a single location. So sometimes there may be resources or components of your parts of your application that don't support this concept of being able to deploy into multiple locations. There are still some applications, some systems that are tied to a specific instance or a server, and they cannot operate in a load balanced fashion. And so if that is the case, in any component, then you want to at least build sufficient scripts around it that if that one piece has a failure, you're able to automate recovery of that one piece in the same location, but on a different instance, say, or in some other way, bring it back to a working state in an automated fashion. So that's an important piece to think about, especially like, data process tools like Informatica, those kind of tools. They won't automatically, they won't support a load balanced model. And so if they don't, then have a script to recreate that instance in an automated fashion. And then using bulkhead architectures to limit scope of impact. This is again an architectural concept where you've got one part of the architecture that is separating out the rest of the architecture from from the front. And so if that front has a problem, then you can just isolate that one piece, but then the rest of the application does not get impacted by that one piece not working. So those are all things that you have to think about and bring into your design as you create the architecture for not just your infrastructure, but also your application. Similar to what we saw earlier, the previous question was around how do you prevent these kind of problems? But when there are problems, how do you design your workload to withstand those problems? So having monitoring on each of the separate components it's an important piece, so you know exactly what's going on across these components. And then when there is a problem, have a process in place to fail over to a healthy resource. This can work when you have load balanced or other systems that can support a failover. And sometimes failovers will they'll change some behavior for the user. And if that is going to happen, then you want to make sure that you've got sufficient communication or expectations being set with the user that a failover happened, you may have to log in again, you may have to try something different. But that's part of the communication that you can perform as part of the way the application is going to function. And then automate healing on all layers, whether it's at the database level, your web server level, your application layer, any of those that can support automated healing, you want to build those in. Not everything will support it, but as far as you can push this, try to build that model into your environment. And then relying on the data plane and not the control plane during recovery is another piece that I don't see happening very often, but it's a very important thought process that we have to build in. The data plane is where your whether it's your database actual data being stored, whether it's whether it's your block storage where you're keeping your hard drives, the information that stays on the hard drive. All of that stuff is your data plane. And that piece is not going to change. AWS has built sufficient reliability and availability within that layer that you don't have to worry about that part. But when your systems or your components go down, you should be able to just recreate that component or redeploy that component and then attach the same storage back to it. So it's back to its functional state with the same data that was there previously. And that's part of what this best practice talks about, that don't think about like making the control plane that's that reliable, that you actually have to spend a lot more money doing those pieces, but rather rely on the data plane so that you can recreate the control plane when there is a recovery that needs to be done. Using static stability to prevent bimodal behavior. This concept, a few different terms in here, but basically you don't want your application behaving differently when there are different conditions within your environment. So if there is a problem, you don't want the application to behave differently in a problem state versus in a healthy state. What you want is you want the application to behave similarly, but maybe the content or the data within that can be different. So that's the nuance that we have to think about. But basically, you don't want the application crashing when there is a problem, and you don't want it like you want the page to still load, but instead of showing the data that was expected, you may show up an error message there. But that's kind of part of the design that you have to think about to say, how am I going to handle how do I design my workload that if one component is a problem, then it doesn't bring down the rest of the application. And of course, being able to notify when there is a problem that's going on, that's an important piece of this design. All right, so now we're coming to the final stage where we're talking about testing. So we did touch upon testing reliability earlier. So load testing is one of those, functional testing, making sure you've got some sort of a playbook that when there is a problem that happens, then to investigate those failures, there's a consistent checklist that you go through, and you're not missing out on something that should have been checked earlier. Performing post-incident analysis is another aspect of making sure that you're becoming more and more reliable as you go through. If there is an incident, some problem did happen, and you've recovered from it, then go back and check, why did that happen? What was the root cause? And how do we make sure that this doesn't happen again? Right. So that post-incident analysis and looking back at what happened and how the team did is really important in making sure that this doesn't happen again, or that the team is prepared in time if that thing does happen again. We've talked about testing functional requirements, pre-deployment, post-deployment, your scaling and performance requirements. That's part of the load testing piece that we talked about. And then testing resiliency using chaos engineering. Chaos engineering is a concept that came recently, like, well, maybe not that recently, but it became popular with Netflix talking about how they use their Chaos Monkey model to inject failure within the environment at random intervals. And what that does is it forces the team to think about what would happen, or how do I make sure that a random outage across any part of my system does not bring down the rest of the application. So that's just sort of a test or a scenario type evaluation that you can do, which is similar to also performing game days, where you actually force your system to have certain problems being injected into it, and then you go through the entire process of not just recovering the system, but also confirming that everybody in the team knows what to do when there is a problem. And so you simulate an incident, and you go through the entire incident response as part of your game day so that everybody gets the practice. It's similar to a fire drill. You just do it regular enough that when there is a real problem, people know what to do. They're not getting, they're not getting flustered at that point to say, hey, am I doing all the right things? They do it with confidence. They can do it with a clear mind and just handle the situation as is required. And then the last piece is around disaster recovery. So what happens if everything goes wrong, goes down, and you really have no way to bring that system back up in that same place? So do you have a way to maintain or bring it up somewhere else? The first question is, what are your recovery objectives for downtime and data loss? They're also known as recovery time objectives and recovery point objectives. Some applications don't care about this, right? They if the application is down, you just inform your users, and when it comes up, it comes up. But some applications which can impact your revenue, it can impact your brand. Some of those things it has a financial component to it. You don't want those things to be down for a long period of time, or you don't want to have data loss happening. So defining what level of risk your business is able to digest, that's an important part of it. And having that definition is going to inform your disaster recovery strategy. It's going to inform even your architecture and design. It's going to inform decisions around how frequently you do your backup snapshots, and it's going to define what sort of regional redundancy you require in your application to make sure that if something does go down, you have a way to recover from it in, say, a different site or a different region. That way, you can successfully recover from that disaster. So you've got a definition. You need to have the strategy for how you're going to meet those recovery objectives. You may just use data being shuttled over to a different region. That's the one strategy, is you have your data being synced up into a different region. And if there is a problem, you just simply redeploy your entire infrastructure into that region. But the entire time, your servers are not running in a different region. It's just data that's sitting there. Another strategy could be that, hey, because of my recovery objectives, I cannot even afford to have that 1 hour time that it takes to reinstantiate everything in a different region. I just need everything up and running right away. And so in that case, you may choose to go with an option of an active configuration or a strategy where you've actually got your workloads running from two different regions at all times. And so if one region goes down, the traffic just gets diverted to the other region, and you're not impacted. Users don't even realize that that's happening, and you just keep going. And then whenever the first region and the application comes back on, you start distributing the workload again as it was earlier. But then testing this process, just the way we were talking about testing recovery from backups, testing your disaster recovery implementation is also an important piece that should be done at least once a year, if not more frequently. It's a more involved process to test a DR plan. So just doing it once a year is sufficient for most organizations. And then managing configuration drift at the DR site or region. That's something we don't end up thinking about too much. But if you've got one active site where you're making all these changes, making sure that those changes will be available to the DR site is something that we want to be conscious about. Sometimes it happens, you make updates to your active site, but the DR site is still pointing to an old configuration or an old setup. And then when a disaster happens, you try to deploy your workloads into the backup region or the DR region, and it just doesn't. It's not compatible. It doesn't work there, and so now you've got a bigger problem at hand, and now you try to figure it out and fix things. We don't want to be in that situation. So having a way to manage the configuration drift is something that you want to think through beforehand. And then the next piece, being able to automate recovery. So obviously that's the ideal state. If any of these things happen, if you're just automatically kick off a DR plan and execute that, that is going to be the ideal way of doing things. It's part of a maturity curve. It takes time for organizations to get to that point. Maybe you do manual recovery the first time, but then now that you've confirmed that everything is working and you've tested it multiple times, then you can just automate those scripts. So a lot of it is going to rely on the kind of tools that you have in your organization, the kind of design that you have in place, but you want to continue to push towards automation of recovery so that the entire team is not brought on call and have to stand by when there is a problem that's going on. So these are all the things that you want to think about when you're doing a disaster recovery. But in general, the things that you want to think about to make sure that your application stays reliable and you're not getting those 2 a.m. calls or being on pager duty and getting pinged in the middle of the night to say, hey, the application is down. Can you go take a look at that? the the questions that we went over, the design principles that we went over from a reliability perspective, they help you as an application owner, as an application team, stay away from those kind of conversations and focus more on building out more functionality and pushing your application forward. So I hope this was helpful. And in the next video, we are going to talk more about the performance efficiency and how to make sure how to use the best practices to monitor and keep checking whether or not your application is performing from a response time perspective to the commitment levels that you have or what you expect it to be. So that's another interesting one that we will talk about soon. Till then, have a good day.